In this episode, we pull together a theme that quietly underpins almost every AI security control we've discussed so far: access control. Access control is the discipline of deciding who can do what, to which resources, under which conditions, and for how long. In traditional security, this shows up in passwords, roles, permissions, and network boundaries. In AI systems, access control becomes even more layered because the system is not a single application. It is a chain of components that handle data, models, tool calls, and agent behaviors. Beginners sometimes assume that if users log in, access is handled, but login only proves identity. It does not automatically guarantee that every downstream component will enforce the right permissions. Applying access controls across layers means you treat every part of the AI stack as a place where unauthorized access could occur, and you design consistent enforcement so the model never becomes a shortcut around your normal security rules. The practical payoff is huge. When access control is layered and consistent, data leakage becomes harder, tool misuse becomes harder, and incidents become easier to contain and investigate. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Let's start with the data layer, because data is usually the most valuable asset and the easiest place for harm to show up. Data layer access control means controlling who can read, write, or retrieve specific information, and it also means controlling how data flows into the model context. For example, if a user asks a question that requires internal documents, the system should retrieve only documents that user is authorized to access, and then only pass the necessary portions into the model. This is a crucial concept because the model itself should not be the decision maker for data access. Models can be persuaded, confused, or manipulated, and they do not reliably enforce complex enterprise policy. Instead, your existing identity and authorization systems should decide what the user can access, and the model should operate only on that approved subset. A beginner misunderstanding is thinking that retrieval is just a helpful feature, but retrieval is also a data access pathway, and if it is not controlled tightly, it becomes a data exfiltration channel. Data layer access control, therefore, includes least privilege, data minimization, and strong isolation between users and between sessions. Data layer access control also includes thinking about where data is stored and who can access those stores, because AI systems often create new storage locations. Prompts might be stored for analytics, chat histories might be retained for convenience, and tool outputs might be cached to improve performance. Each of those is a data store that needs access controls, retention policies, and auditing. If you do not treat these stores as sensitive, you can accidentally create a shadow database of private content that many people can access, such as developers, operators, or analysts. Another risk is cross-tenant leakage, where one user's stored context is accidentally used in another user's session. This is why isolation is part of access control. You are not only controlling who can query a database, you are controlling whether the system can correctly separate user contexts at all times. For beginners, the key idea is that every place data is stored, even temporarily, is a place where access controls must exist and be enforced consistently. Next is the model layer, which includes access to the model service itself and access to specific model capabilities. Model layer access control begins with who can call the model endpoint, and it often includes gating by application identity, user identity, and environment. For example, you might allow only the backend service to call the model, not user devices directly, because that centralizes control and reduces key leakage. You might also separate access by role, so only certain users can use a high-capability model or a model that can handle sensitive data. Model layer access control can also include feature controls, such as whether certain users can use longer context windows, whether certain users can enable memory, or whether certain users can request certain output formats. The reason this matters is that model capabilities can expand the blast radius of misuse. A model that can generate code, handle files, or plan actions can be more risky than a model that only summarizes text. Access control at the model layer is about matching capability to need, so not everyone gets maximum power by default. Model layer access control also includes managing model versions and ensuring that access decisions are stable across changes. If a vendor updates the model behind the scenes, you might see shifts in refusal behavior or output style that change how safe the system feels. If you pin versions, you gain predictability, but you also need a process for upgrading. Access control plays a role here because version upgrades can be restricted to controlled environments first and only later promoted to production after validation. In other words, who can change the model version is itself an access control question. Beginners sometimes think of access control as only about users, but in secure operations it also covers who can change critical configuration. If the wrong person can switch the model or disable safety features, that is an access control failure that can lead to system-wide risk. Mature systems therefore treat model configuration changes as privileged actions with approvals and logging. Now we move to tools, which are often the most dangerous layer because tools connect the model to real systems and data. Tool layer access control means the model can never freely call tools with broad privileges. Tools should require authorization checks outside the model, and tool credentials should be scoped to the minimum operations required. A strong pattern is that tool calls are executed by a service that enforces policies, not by the model directly. That service checks the requesting user's permissions, the allowed tool set for that role, and the allowed parameters for that tool. For example, a document retrieval tool might allow searching only within approved repositories for that user, and it might limit the number of documents and the size of excerpts returned. A write-capable tool might require human approval before execution, especially if it can send messages or change records. The key beginner insight is that tool access is privileged access. If you treat tools casually, you will eventually create a path where a clever prompt can trigger an unauthorized action. Tool layer access control also includes controlling what tools are available in which contexts, because context switching can create unexpected paths. For example, a user might start in a low-risk chat that is meant for general questions, but then attempt to trigger a tool call that accesses sensitive systems. If the system exposes the same tool set everywhere, it becomes hard to reason about safety. A more secure approach is to limit tool availability by workflow, so a low-risk interface has no right tools, and a high-risk interface has carefully scoped tools with approvals. This reduces the chance that a user can accidentally stumble into a powerful capability they do not understand. It also reduces the chance that an attacker can use the easiest interface as an entry point to powerful actions. Another important tool control is separating tool credentials by environment and by tool, so that compromise of one tool path does not automatically compromise others. For beginners, it is enough to remember that the safest tool is often read-only and scoped, and any right tool should feel like a serious capability that requires strong justification and strong controls. Agents are the final layer, and they are where access control becomes especially subtle because an agent makes sequences of decisions over time. Agent layer access control is about limiting what the agent can decide, limiting what it can attempt, and requiring checks at each step. An agent should not be able to grant itself permissions, and it should not be able to escalate privileges just by reasoning about them. The agent's plan should be constrained by policy, and tool calls should be authorized independently at execution time. This is important because an agent can be tricked into making a plan that appears reasonable but includes an unauthorized step. If the system only checks authorization at the beginning, the agent might later attempt a step that is not allowed, and without per-step checks it could succeed. Agent layer access control, therefore, includes session scoping, meaning the agent's authority exists only within the boundaries of a session and it expires. It also includes memory controls, meaning the agent should not carry privileged context across sessions in a way that can leak or be reused. Beginners should recognize that in an agent system, access control is not a single gate. It is repeated enforcement throughout the chain. A useful way to tie all layers together is to think in terms of a consistent permission story. The story starts with a user identity, which might be an employee or a customer. That identity has roles and attributes that define what they are allowed to do. The system then uses that identity to control data retrieval, model capability, tool availability, and agent actions. At no point should the model be able to invent permissions or to bypass the story. This is why identity propagation matters, meaning the user's identity is carried through the system in a trusted way so downstream services can enforce policy. If identity is lost and replaced with a generic service identity, you risk giving every user the privileges of that service. That is a classic misconfiguration that can lead to broad data exposure. The secure approach is to keep authorization decisions centralized and consistent, and to ensure that every layer respects those decisions. For beginners, the big takeaway is that a single weak layer can undermine all the others. If the tool layer ignores user permissions, data layer controls are bypassed. If the agent layer can call tools without checks, tool layer scoping is bypassed. Access control must therefore be end-to-end. Auditing and accountability strengthen access control because they help you verify that policies are actually being enforced and help you investigate when something goes wrong. Across layers, audit trails should record who requested what was accessed, and what actions occurred, along with model versions and tool usage. This does not mean storing every prompt in plain text forever. It means having enough evidence to answer key questions during an incident without creating unnecessary privacy risk. Auditing also supports improvement because it reveals patterns, like which roles frequently hit access denials, which tools are most requested, and where users try to push boundaries. Those insights can guide policy refinement and user education. Access control is not only about blocking. It is also about shaping safe paths so legitimate work is supported without risky shortcuts. When auditing is strong, you can tune controls based on evidence rather than guesswork, and you can demonstrate compliance with security requirements. As we conclude, applying access controls across layers is the difference between an AI system that is merely authenticated and an AI system that is truly governed. Data layer controls ensure users only access what they are permitted to see and that sensitive stores created by the system are protected. Model layer controls ensure that model endpoints and capabilities match the user's role and the system's risk posture. Tool layer controls ensure that tool calls are scoped, authorized, and logged, so the model cannot become a backdoor into real systems. Agent layer controls ensure that multi-step behavior remains bounded, checked, and reviewable, rather than drifting into unauthorized action. When these layers work together, the system stays within safe lanes even under adversarial prompting and operational pressure. The core beginner lesson is that AI security is not about trusting the model to be wise. It is about building a consistent permission story that the model cannot rewrite. If you can explain how access control must be enforced at each layer, and why losing that enforcement at any one point is dangerous, you have a strong, practical understanding of how secure AI systems are actually operated in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.